This is a short discussion of satellites in circular orbits. So we have a picture here shown to the right where we have a satellite moving around the Earth in a circular orbit. As it moves in this circular path, there is a centripetal acceleration towards the center of the circle. The satellite travels with a velocity v, and it revolves around the Earth with a radius r. And we also have the time that it takes to complete one cycle, which is called capital T for period. So as this satellite revolves around the Earth in a circular path and continuously changing its velocity because it changes direction, there is some force that is causing it to move in a circular orbit. And in this case, this is the gravitational force that is pulling the body towards whatever body it's revolving around, and in this case would be the Earth. Now we can apply this to many examples. So we can apply the same example to not only just man-made communication satellites, but you can apply it to the moon, or you can even apply it to planets that are revolving around the sun. Now technically planets don't revolve around the sun in circular paths, they are in elliptical paths, but in some cases the planets revolve in nearly circular paths, and so we can apply these principles here that we're about to develop. So let's now review Newton's universal law of gravitation, which is shown right here. Newton's universal gravitation law said that any two particles in the universe will attract each other, and their magnitude of the force of attraction is directly proportional to the product of their masses and inversely proportional to the square of the distance between the two bodies. You'll note that the force of attraction on both of these are the same, equal and opposite, just like Newton's third law. So if we apply this to the Earth and the satellite, there is a gravitational pull that is pulling the satellite towards the Earth. There is also a gravitational pull of the Earth towards the satellite. These are equal and opposite. But remember that the Earth has much more inertia than the satellite, so its acceleration towards that is negligible. And so really, we're only going to be looking at the acceleration of this satellite as it revolves around the Earth in a centripetal direction. So we can use Newton's second law, which is shown here, for this body m, which is the satellite's mass. And the only force that's causing it to move in this circular orbit is the gravitational force, Fg. Now Fg, you may recall, we can calculate as mg, but little g is only 9.8 if you were on the surface of the Earth. So really we need to use Newton's universal gravitational law with g, m1, m2, all over r squared. So in this case, m1 is really the satellite mass, and m2 is the Earth's mass, and r is the distance from the center of the Earth to the satellite. Basically, its radius of orbit. So we're going to set Newton's universal gravitational force equal to the net centripetal force inwards. And you'll see that the m of the satellite cancels out. And one of these r's cancel out as well. And you get the following expression that the velocity of orbit is equal to the square root of the gravitational constant times the mass of Earth divided by the radius of orbit. So you notice, by the way, that the mass of the satellite has canceled out. It has been algebraically canceled. The greater inertia of the more massive satellite, so if you had a greater mass here, is overcome by a proportionality of greater gravitational force acting on it. So that's why the m here will be bigger, even though we'll have a greater centripetal force, so the m's cancel out. Also, I think it's important to note that the speed of the satellite does not depend on the mass. So you do not, if you have a bigger mass, it will not need to be going any faster. However, it does depend on the radius of the orbit. So if r is smaller, then velocity will have to be faster as it revolves around the Earth. So if I just look down below here, we have a little discussion about projectiles that are fired from, say, you had a very tall tower here, and as it falls towards the Earth. Now if you fired a projectile and it wasn't fast enough, then we have just projectile motion, which is 1 and 2. If you fire it with enough speed to basically match the Earth's curvature, then it'll follow path 3. But path 3 is not quite circular, it's actually elliptical. If you fire it just at the right orbital velocity, then it'll follow path 4, which is a perfect circle, and then a little bit faster than that, then it goes back to elliptical paths. And then, if you fire it even fast enough so that you can finally get away from the Earth's gravitational pull, then you'll go along paths 6 and 7, which will then spiral away from the Earth. We'll study 6 and 7 a little later on when we talk about what's known as the escape velocity. And I can't explain that at this point in this chapter because it involves the use of conservation of energy. And that comes in next chapter. So let's now move on to the next page, and so we can describe how we can relate the radius of an orbit to the period of a satellite, the time that it takes to make one revolution around the Earth, for example. So earlier we derived this equation, the velocity of orbit. And so now what we're going to do is we're going to substitute in the following equation, which is the velocity equals the distance around the orbit, which is the circumference, 2 pi r, divided by the period, the time that it takes to make one revolution. So if we substitute that into the equation, 2 pi r over t, or rewrite it as t equals 2 pi r over v, we'll get the following expression, which is shown here. And this is known as Kepler's third law, which is shown right here below. You are responsible for knowing the derivation of this. So you are responsible for starting from first principles using sum of f equals mac, mv squared over r equals g m all over r squared. You can make a few cancellations here. We have g m all over r equals, now we'll substitute v as 2 pi r over the period squared. This then becomes the following: 4 pi squared r squared all over t squared. Once again, we can rearrange the equation as shown here. So we can rewrite this as t squared equals 4 pi squared all over g m of whatever body that the satellite is revolving around times r to the power of 3. You have an r squared here and an r. So we can see that t squared is directly proportional to r cubed. So you have to know this derivation. It's part of the Physics B curriculum. This bit right here is really a constant. So Kepler studied the planetary motion of planets around the sun, and he noticed that they obeyed this law, that their period around the sun squared was proportional to the radius of orbit cubed. For each planet, whether it's Mars or Jupiter or Earth, they all obeyed this law. Kepler formulated 3 kinematic laws of planetary motion. The first law is that the path of any planet will be in an elliptical path, with the sun at one focus, as you can see here. So when you know in an ellipse there are 2 foci. So the sun would be located at one focus, and this is the planet as it revolves around the sun. Or it could be a comet, or any astronomical body revolving around the sun. His second law said the following: if you were to connect a line that joins between the planet and the sun, so this line right in here that's shown, it will sweep out an equal area over an equal time interval. So if you were to look at area 1 and area 2, they would be both the same area as long as these two were the same time period. So the time that it takes the planet to go from 1 to 2, say it could be, I don't know, a couple months, like 2 months, then this is also 2 months. You'll notice that it doesn't travel as fast or as far because it's further away. There's less gravitational pull, but the area that it sweeps out will be equal. So that's the second law. And then the third law, which is the most important one that you need to know, is really Kepler's third law. Here shown that the time period of it as it goes from 1 to 2, or the time period as the planet goes around the sun squared, is proportional to the radius, the average radius from the planet to the sun. And that's it for this discussion of satellites and Kepler's laws.